lecture. Today's lecture, it will be the last lecture of our Fourier series. We'll go also through the Parseval Theorem. So the readings in today's lecture, which is page 216 to 218. Then in Wednesday, as I told you, this is going to be a lecture for exam 2 return and the answers. Again, the TA is a graded exam, so I did it graded, so I encourage you to reach the TA if you have any problems about the grades. If you, after reaching the TA, if you still have some problems, please you can reach me by email. Friday, we will start a new topic, which is Fourier transform. Fourier series of Fourier transform. Fourier series most likely been used for periodic signals, while Fourier transform can be used for non-periodic. And the readings from page 218 to 222. And this one will be, this course, or this lecture will be taught by another instructor, so there will be no recording. Another instructor will teach. There will be no recording, so please make sure to attend this lecture. So I will be traveling from tomorrow, Tuesday, I'll be back on Friday in the afternoon, so I will be traveling this time. So I might not be able to reply to your emails. So the deadline, I think, for reviewing the grades is Friday for the TA, but in case, if you have any problems, I can extend it to Monday. Okay, because I will be traveling, I cannot reply to your emails. But I would say, even though the deadline is Friday, but if you have any problems about the grades, I can do it on Monday. But this is after reaching the TA. So in case if when you reach the TA and you are not satisfied with something, or you still think this is unfair, is there more point, then you can reach it, and I can solve the issue. Okay, so in Monday, which is in April 8th, I will be back. So I will be back actually Friday afternoon, so Monday I will be able to teach. So the readings continue for this series, page 218 to 240 transform 222. And I forgot to mention the due date for homework number 12, which is going to be this Friday, I'm sorry. And the MATLAB 2, MATLAB 3 project, this is the last MATLAB project, which is going to be on Monday. All of them are in for your series, so it should be fun. Okay? Any questions? Again, Friday lecture will not be recorded. And Wednesday, of course, there will be nothing new, just like we're going through the exam. And there the only thing that I might provide you is the lecture notes. I can't provide you the lecture notes. Other than that, the recording will not be available. Last lecture, we started Fourier series on the pulse train using the exponential representation. So we already said this is the exponential representation, then we find the XL by substituting k equal to 0. Then when we did the calculation, we found XO equal A over T times L. We said this is the same as A0, which is the DC value. That's what we discussed last lecture. Then we said we need to find xk for any value of k, no matter if it is 0 or not. Then we did this integral, which is basically the integral from negative t over 2 until t over 2. Then when we look at the pulse, we can divide it into 3 areas. The first area, when you are moving between negative t over 2 over tau over until tau over 2. This is the integral of 0. The area of 0 is 0. Then there is no need to put it. Then the second area, between negative tau over 2 until tau over 2. This is the actual integral area. Then the last one, which is between tau over 2 until t over 2. So this will be 0 as well. So because there is nothing to integrate. So we did last lecture, we did 3 integrals into 3 areas, and we said these with the left and the right, both of them are zeros because you integrated nothing. Then the only remaining thing, which is in the middle. And in the middle, it is the amplitude is A, So you are making the integral from negative tau over 2 until tau over 2, a equal negative jk omega naught t dt. Then how to do this integral? It's just basically an integral of the exponential. So we put a outside of the integral, so it will be a over t. Then the integral from negative tau over 2 until tau over 2. Then after evaluating this integral, the exponential, then substitute negative tau over 2 and positive tau over 2. Then when we include the negative j, put it inside the brackets, and recall Euler's formula, sine theta equal e for j theta minus e for negative j theta over 2. We have a negative here, we will put a negative so to flip the exponentials. So it will be 2a over k omega naught t equal j theta minus e for negative j theta over 2j. This is the definition of sine. So it will be 2a over k omega naught t sine k omega naught t. That's x sub t. Okay? Now we can simplify it more. I mean, here we should be done. But I'm gonna just simplify it more. We can simplify it by dividing it as so a or x sub k equals to a tau over t times sine k omega naught. Let's see here, I think I wanted to mention when we do this omega naught tau over 2 or here tau. Let's please make this correction. So like this, just over here. So sine k omega naught tau over 2. So what I'm gonna do, I'm gonna say let's make here divide, multiply x to a. So I'm gonna multiply by tau over 2 over tau. I'm gonna write it. So I just isolate this, so here it will be k omega naught. I just try to play with the terms. I put k omega naught on one side, 2a over 3 on one side, then I'm going to multiply by pi over 2 on both sides. And doing a denominator by numerator. So it will be tau over 2 times 2a will be a tau over t. Then sine k omega naught tau over 2 divided by k omega naught tau over 2. Okay, what's the point of this step? This is the same as this one, right? This looks like sine x over x. And what's sine x over x? If we do this, we already discussed this. Same function. We do the same function. Same x. We already discussed this. I'm not sure. Same function, which is sine x over x. So basically, we can say it will be a tau over t sine k omega naught tau over 2. That's it. And we can say, we call x naught, we defined it as a tau over t. X naught, which is the one that we calculated here. A tau over t. So we can re-simplify x sub k will be x naught sine k omega naught tau over t. So that's it. This is another representation, so both of them, no matter if you use the first one that we found or this one with simplification, both of them are correct. So in summary, x of t will be the sum from k equal to negative infinity to infinity substitutes xk by x naught sine k omega naught tau over 2 e power j k omega naught t. This is the Fourier series in the exponential. Then problem 1. If you want to substitute sec of k, x of k, the other one that we box it, which is the first one, this is correct. So no matter what we're using, but here I just show you the simplest way. That's how we do it. That's how we simplify it all. Yeah? Any question? Let's recall the same. We already discussed this one, now we'll go into more details. Recall the same function. So we discussed the sinc function as sinc of x as sine x over x. That's what we know. That's what we discussed in previous lectures. So this one, we call it normalized sinc function. There is another representation of sinc function, the same as sinc function, that we want, sinc of x, but it is sine of pi x over pi x. We just included pi. And this one is called the normalized sinc function. Normalized sinc function. Because in that one, whenever we are dealing with sinc alone, recall it will be like this. Then the intersection will be, if you are with sinc alone, pi, 2 pi, 3 pi, etc. Here, negative pi, negative 2 pi, negative 3 pi. If you are working with unnormalized. What's the point of using normalized? In normalized one, you will not see the pi at all. So it will be as, for example, like this. It will be, here is 1, the intersection will be instead of pi, 2 pi, 3 pi, 1, 2, 3, 4, here negative 1, negative 2, negative 3, etc. So just that's it. The normalized, we don't want to use pi on the time axis. We just say 1, 2, 3, negative 1, negative 3. However, if you are dealing with the unnormalized, then you will say pi, 2 pi, 3 pi, or negative pi, negative 2 pi, negative 3 pi. That's the only difference. Otherwise, they are pretty the same. Keep in mind, in MATLAB, they are using the normalized, which is whenever you say sinc of x, this means sine pi x over pi x. That's the MATLAB. So the sinc function inside the MATLAB tools will be based on the normalized, which is basically the intersections is 1, 2, 3, negative 1, negative 2. So keep in mind, it will be pi x, not x. So some properties of the sinc functions, I think you're already familiar, but just keep in mind what will happen at the origin 0. At the origin 0, it will be 1. Sinc of 0 will be 1. So sinc of 0 will be 1. How? Which is basically it is sine 0 over 0. And sine 0 is actually 0. 0 over 0, this is invalid. How to find sine x over x? Basically we need to find limits sine x over x such that x goes to 0. How to find this? Yes, exactly. So basically you take the derivative d by dx of sine x over d by dx of x, which will basically limit when x goes to 0 cosine x over 1 up it's going to be as cosine 0 over 1, which is 1 over 1, then it will be 1. Therefore, as a result, sin of 0 will be 1. And we already know this from the properties, but here just like the proof. Okay. Then the other thing is number 1, number 2. Sin k pi such that k does not equal to 0. Okay? We will not say, because when k equal to 0, we know sin of 0 will be 1. So we have different values like plus minus 1, plus minus 2, etc. How we can find it, basically, it will be, I'm going to use the unnormalized, which is sin pi x will be sin k pi over k pi. So sine k pi, sine anything k pi will be 0 over k pi 0. So sin k pi equals 0 for all k does not equal to 0. As a result, we can conclude when we plot the sin function, when it is at 0, it will be 1. When it is at pi, 2 pi, 3 pi, all of them will be zeros. The function will be zeros. Then the same, negative pi, negative 2 pi, negative 3 pi, all of them will be zeros. That's how we conclude, how we find it. Then you can connect between them. So it will be like this. Then by decaying it. Okay? Again, in MATLAB, they are using the normalized, which is whenever we say sin of x, this means sine pi x divided by pi x. Now, how about if I want to use the unnormalized? What should I do? Assume your own sin. So basically, let's assume unnormalized. Build your own. Build your own. So basically, we will say function y, here is I'm defining the function, equal to, I can call it my sin, which is that's my own sin. My sin, and the input is x. So, we will say like, if x equal to 0, you know this, if it's equal to 0, then y will be 1. To make sure we will avoid 0 over 0. Y equal to 1. Then else y equal to sine x over x. So I didn't put direct sine x over x because to avoid the, when it is 0, it will give invalid. Then n. So you will store this in M file. And call that M file, the name is my sin. Okay? You can either store in M file or include it in the code. I encourage you to store it in M file. That's how we build my own sync. Then you can say like my sync. My sync. Let's go back to this example here, and we realize that the function, the output, will be a sync. So how this looks like in time domain and just a comparison between this is the time domain, how it looks like in frequency for the pulses. So I'm going to plug it here just as a demonstration for your knowledge. So, pulse train spectrum. When you see spectrum, means in frequency. But here, let me write the time domain first. So time domain here is t, here is also t. Then we have a pulse between tau over t, here tau over t, and it is centered at 0. Then we have at t, we have another pulses, so centered here. And at negative tau, negative t over, we have another pulse center here, such that the distance from here to here tau, the distance from here to here tau, or otherwise from here to here tau over t, from here to here tau over t. So you can say t minus tau over t. Here is t plus tau. And the same thing here, we can say this is tau over t, tau over t. So here is negative t plus tau over t, here is negative t minus tau over t. Okay, and the amplitude is 1. This is time domain. Now how it looks like in frequency domain, it will look like we will put an envelope as a sink. This is the envelope. Because we know the factors will be as sink. Then the other signals or the other components will be like this. So here is F0, F0, etc. That's how it's functioning. Which is basically what you will see in the blue, this is the actual outputs. But what you see in the red, here is the dots, which is the spectrum, means it will be bounded between this boundary. So it's like, we call it envelope, which is the output will not violate that envelope. Will be within the envelope. So you can forget about the red and look only at the blue. And the blue, that's the waveform how it looks like. And of course, F0 to F0, etc. And here is the origin. And again, F0 related to the period. So the envelope will say this is how that looks like, or the spectrum looks like. Even though it's pulse, the time domain, but frequency domain, it is a sync function. And you will see this a lot when you go to the communication signals. For example, when you go to communications, for example, you will see this maybe in ESP or some of those courses. Any question? There's a MATLAB program about how to make a pulse string using the Laplace, or using the exponential form of Fourier series, and we see that how we define the magnitude of the pulse, magnitude of the pulse width, the period, number of points that we need to do, because remember, we cannot plot forever until infinity, so we need to determine like how many numbers, period, and how many points we need to do. Then this is how we put the function, then basically see, okay, to find, or we calculate xk here, to calculate the sync, or to calculate the Fourier coefficients. Then we can plot it. Then plots, and when we assume tau equal 5 seconds, this is how it looks like x of t, which is the time domain. And you look at ck, or in other words, we call it xk. This is the the magnitudes of the Fourier series. So we can see whenever we have tau equal 5, we get something like that. So which is something similar to sinc. At the origin would be the max, then it will probably be reducing, similar to sine wave. If you assume tau equal 25, you will see a narrower pulse. Then a narrower pulse, you will see how this will affect into the number of samples, because the number of sinks, when you have a 25 time, this means you will increase the number of samples that are sinks. Okay. Then let's go to the next one, which is Parseval snatch. Parseval. So Parseval theorem is related to the power of the signal, which is how much the power of the signal. Power of x of t, a signal x of t. So in time domain, how we can calculate the power? Basically, we can say px, this means power of x of t, that's why I call it sub x, equals to 1 over t, the integral from 0 to t. This is something similar to the average integrals from 0 to t, but we will use the absolute value x of t squared. Okay? So it is something similar to the average, but we will make a square, x of t squared. The integral for all the full period, but we will make a square. This is in time domain. Now, how can we find this if we are in phasor domain? Most likely in time domain, sometimes it can be harder analysis, but if we do this in frequency domain, it will be much easier. How? Let's see case number 1, when we are with complex exponential Fourier series. So complex exponential Fourier series, I see number 2, because number 1 time. Basically, it says that x of t equals to the sum from k equal negative infinity to infinity, x sub k e power jk omega naught t. Then, basically, the power of that signal will be the sum x sub k when k equal negative infinity to infinity, or the absolute value of x k squared. Okay? Just take xk and take the square of x. The absolute value of it and take the square. Why? Because the exponential, if you take the absolute value of exponential, every time will be 1. We know that. And 1 squared every time will be 1. The absolute value or the magnitude of e power j theta, e power theta, whatever it is, every time it is 1. Why? E power j theta equal cosine theta plus j sine theta. The absolute value of cosine theta squared plus sine theta squared will be 1, right? Just take forward. E power j theta equal cosine plus j sine. Then to take the magnitude e power j theta will be cosine squared plus sine squared, and this is equal to 1. That's the proof. So every time e power j theta, or e power theta, the magnitude e power j theta every time will be 1. Then px will be the absolute value of xk squared. So we don't have to know x squared, right? So this is, again, this is frequency domain. Then we have other types of Fourier series. We have the third one, or the third one, which is the Fourier series with magnitude and angle. Magnitude and phase Fourier series, which is basically was built on x of t equals a0 plus sum k equal 1 to infinity, ck cosine k omega naught t plus pk. So what's the magnitude, or what's the power? So the power here will be A naught square plus sum when k equal 1 to infinity ck square divided by 2. Okay? Let me box this. This is time, this is compass, presentation, this is phase and magnitude. Then we have number 4, when we are dealing with the other form, the third form of Fourier series, which is sine, cosine, Fourier series, which is basically sine cosine x of t equal to a0 plus sum k equal 1 to infinity a sub k cosine k omega naught t plus b sub k sine k omega naught t. Then how to find the power, which is basically, it will be a naught squared plus the sum from k equal 1 to infinity a sub k squared plus b sub k squared divided by 2. Okay? A squared plus b squared divided by 2. So this is number 4. So we have 4 ways in calculating the power of that signal. The power of the signal can be like similar to the average 1 over t, the square root from 0 to t, x squared t, or we can say in frequency domain we have 3 different ways depending on your available Fourier series. If you have this in sine cosine, it will be a naught squared plus the sum a squared plus b squared over 2, or if you have phase and magnitude, it will be a naught squared plus the sum of c squared divided by 2, or the last thing, if you have it in exponential, it will be the sum of kx squared. So we have 4 different ways in solving the complex solving the power of that signal. Okay, this is the power of the signal. And I think you are already familiar with power in circuit analysis, which is, we used to say, this is V times I, right? We used to say in circuits, P of t equals V of t times I of t, something like that. This is the instantaneous with the time, not the phase of the time. Then we can apply Ohm's law for a resistor such that I of t will be V of t over R. So we can say P of t equals to V of t squared divided by R. Something like that. This is the power. Or it can be I squared I of t all squared times R. Okay? That was the real power. Then we used to say there is something called an average power. So such that P average, then what we do is we just do the integration 1 over t, the integral from 0 to t, V of t squared dt divided by R. Or we can say, if you are using time, P 1 over t, the integral from 0 to t, I of t squared dt times R. Okay? Then how we can do this analysis depending on the signal. So basically, before we will do the time domain, if we are dealing with sinusoidal, then we can use what we know, what we learn in circuit analysis. But the point here is, how about if I have a pulse signal, square wave, not sinusoidal source? How can I find the power? We can use the theorem, which is converted to find Fourier series and find the analysis of the Fourier series, or we can do the integration, whatever you want to do. How about if it's triangular, sawtooth? you can find a Fourier series to it, and you can find a power in an easier way. So again, when we are dealing with non-sinusoidal, it will be more complicated signals. Therefore, to find the average power, this is the overall formula. Okay, any question? So that's the theorem. Now let me run an example of the power. So I'll give you a few seconds to write. Then we will go to the example. Example. Assume we have the following signals and we need to calculate the power. Let's assume that you have sometimes non-sinusoidal, or you can have signals that combination of sine, cosine, whatever, maybe different frequencies as well, different phase shifts. No matter what it is, we need to calculate the power of that signal, such that we have a signal called x of t equals Cn cosine n omega naught t plus phi n. Y of t equals Cm cosine m omega naught t plus phi n. You can realize that here is m, here is n. So basically, these x and y have different frequencies, are working on different frequencies. This will create some problems. Basically, the circuits techniques that we have learned in circuits course cannot be applied here. So that's here's the advantage of using signals and systems in solving these problems. Then z of t equals to what? I'm going to assume another third signal a naught plus a combination x of t plus y of t. So here there's a naught, a naught, cn, cn. All of them are real numbers. And every time we'll assume m and n integers are integers. And we will assume m does not equal to n. So we will not go to a way they will equal to each other. Basically, x and y are working with different frequencies. So this one working with other frequencies, the other one with m frequency, this one with n frequency. So they will not, the frequency for both will not be equal to each other. So the question is compute px, py, pz. P sub x means the power of signal x. Py, the power of signal y. Pz, the power of signal z. So how to compute this? Let's start with x. P sub x, according to the formula, it is 1 over t, the integral from 0 to t, x of t squared dt. I have a time domain expression, so I'm going to use the time domain expression. There's no sum, there's no Fourier series, so let me try the time domain to see. So substitute t, x, which is 1 over t, the integral from 0 to t, cn as a magnitude squared, cosine squared n omega naught t plus phi n dt. Cn is a constant, so I can put it outside of the integral. So it's going to be 1 over t, Cn squared, then the integral from 0 to t, cosine squared of n omega naught t plus phi n dt. Now, what's the cosine squared, the integral of cosine squared? What does it equal? Let's go to table 5.2. So you'll see it will be t over 2. Table 5.2, which is some integrals. They are all going to change. The integral of cosine squared t naught over 2, so from 0 to t will be t over 2. That's here, so let me go back to the lecture now. So it will be t over 2. So as a result, it will be 1 over t Cn squared times t over 2. T and t cancel each other, so it will be 1/2 Cn squared. This is the power of signal x. Okay? Does this make sense? Now, the next thing is to calculate the power of signal y. But let me give it time to write, and we will go to signal y. Okay, the power of signal y is very similar to signal x in the concept, which is 1 over t, the integral from 0 to t, y of t squared dt, which is going to be 1 over t, the integral from 0 to t, Cm as a magnitude squared, cosine squared m omega naught t plus Vm dt. Put Cm outside of the integral will be 1 over t, Cm squared, the integral from 0 to t, cosine squared m omega naught t plus Vm dt. And this cosine, according to table 5.2, equal to 2 t over 2. So as a result, it will be 1 over t, Cm squared, t over 2, t and t cancel each other, which will make it 1/2 Cm squared. This is very similar to x. It was 1/2 Cm squared, now it's 1/2 Cm squared. So even you don't need to calculate it. You can say 1/2 Cm squared and that's it, because it's very similar, but with different notation. Now the third one, which is the power of signal z. The power of signal z, according to the formula, 1 over t, the integral from 0 to t, z of t squared dt. Then, substitute z of t, 1 over t, 0 to t. So I think this is more math, more than signals. Cm cosine n omega naught t plus Vn, then plus Cm cosine m omega naught t plus Vn, all of it squared. So we need to do that. Let's do the square first, then we can get the answer. So how to do the square of this? L 1 over t, the integral from 0 to t. Okay, so we have here a naught squared plus Cn squared cosine squared of n omega naught t plus Vn plus Cm squared cosine m omega naught t plus Vn, all of the squared. Then we get the square of this term. Then there will be a 2 combination, a and Cm, a and Cm, Cm and Cm. So there will be another 3 pairs of each one. So plus 2 plus 2 plus 2. So the first one with a naught Cn cosine and omega naught t plus Vn. Here I'm doing the square for all of this term. Then here plus a naught Cm cosine n m omega naught t plus Vn. Then the other one, which is Cn cosine n omega naught t plus Vn, then plus times cosine m omega naught t plus then don't forget to write dt. All of them are inside the. Now we have a trigonometric calculation. So let's go term by term. The first term, a naught is a constant. So the integral of that constant will be, I can say 1 over t of that first one, which is a squared t minus 0, which is a squared times t. Now the second term, cn squared, then we have the integral of cosine squared. We already agreed that it will be 2 over 2, t over 2. Because again, table 5.2. Then the third term, cm squared cosine, so it will be cm squared t over 2. How about the cosine and omega naught t? The integral of the cosine alone is 0, right? For the full period. So it is plus 0 because the cosine. But then the next one, the integral of the cosine is also 0. So here is 0. Then the last one, which is the integral of cosine times cosine, such that n does not equal to m. It will be 0. That's given in table 5.2. Let me go through it. Sine times cosine such that m does not equal to 2. The n does not equal to m, it will be 0. So let's go back here. Then it will be plus 0. So the only terms remains the 3 terms, while the rest are zeros. So the answer will be 1 over t, the integral of a squared t plus cn squared t over 2 plus cm squared t over 2. We can take t as a factor, then it will be cancelled. So t, cancel t, cancel t, cancel t. And take 1 half, or you can just the one distributed, then it will be pz will be a naught squared plus 1 half cn squared plus 1 half cm squared. That's it. That's it. Okay. Does this make sense? Any questions? Yes.
So what are we taking the power of? Is this like finding the average voltage, or where is the power coming from?
Yes, so here, like, we know the power in circuits, which is V times I or something like that. But now, we will assume that we have a signal, which is basically a voltage signal. So we need to calculate the power of that signal. So this is can be, we can use it like for communication, especially communication signals. Then we need to calculate the power. Basically, we can apply this formula, which is 1 over t for all square dt. So you can realize that when I mentioned about the power here, for example, the voltage, v squared over r. So r is constant. So no matter what r it is. So we can assume that for example, the situation r at like 1, then you can calculate the power, which is as the average voltage. Any other question? Okay. This is the end of Fourier series. Next lecture, Friday, there will be Fourier transform. So see you on